Hello. Good day, everyone. Please, can you hear me?
Yes, we can hear you. Thank you.
Uh, Good day, everyone. My name is Abdulmalik Adamu. Um, Today, I will talk about the introduction to train aerodynamics. In this seminar, I will discuss about aerodynamics, train aerodynamics, and then train aerodynamics problems. And I will go ahead to talk about the research method in which train aerodynamics are being studied, which include full-scale tests, reduced-scale tests, and computational fluid dynamics. Then in the third section, I'll talk about the result analysis, how to analyze the train aerodynamic problems. These I'll talk about the forces, flow field, pressure distribution. Then in the last section, I'll conclude. So aerodynamics is a branch of physics that studies the interaction between a fluid and a solid body. It is defined external if it analyzes the flow around the bodies. These include problems including aeronautical and automotive fields, also including civil engineering problems. These includes the flow around the body. This flow can be either a flow around a car, for example, it's as seen in this picture here, or high-speed train, as we are going to discuss in this seminar, or externally of a building, as we can see here in this picture also, or it can be internal if it deals with flows inside the body. This includes inside an engine, for example, air conditioning system inside a building, and so on and so on. So train aerodynamics is the key basic science that aims to study the problems of trains, most especially high-speed trains. So in train aerodynamics, what we normally study is the flow externally or internally of a train. This study is aimed at providing either comfort, safety, or energy conservation. So train aerodynamic problems. So these are the problems that we normally will solve when we study train aerodynamics. This includes energy consumption. So here we are going to talk about aerodynamic forces. These include the drag force, the lift force, and the side force. The second problem is safety. So we want to ensure safety when the train is moving in a windy environment. That's crosswind stability, or we want to also ensure that is being operated safely, like people that are standing close to the railway infrastructure as the train is being operated. So we also study the slipstream around the train. So also we study the problems when two trains meet as these two trains are being operated. So we talk about the train meeting operation. And also we solve problems that deals with the train and the infrastructure. So because as we know that as the train moves, it moves also with a lot of air. So this air, when impacted with the infrastructure, may cause damage to some of the infrastructure. So we also study the train and infrastructure aerodynamics. This includes the train tunnel aerodynamics or train embankment aerodynamics or the train track aerodynamics. So the next is the comfort. This includes an external noise. That's a noise that this what the train is going to generate when it's being operated. This includes noise that will emanate from the bogie areas, from the intercarriage gaps, and so on and so forth. And the internal noise, which includes the noise in the cabin, which is being generated by either there is maybe a kind of from external problems, which is being transmitted into from external noise, which is being transmitted to the inside of the cabin. And also, we talk about we also deal with a ventilation system, the comfort, how air conditioning system are being operated so as to ensure good comfort. So what are the solutions to these problems? So for energy utilization, that's the aerodynamic forces problems, we ensure that we optimize the shape. These optimization of shapes have been done for severally in different levels. For example, the first optimization that is more obvious for many people is the head shape optimization, whereby we different manufacturers and researchers try to recommend different head shape. This head shape optimization has helped us to reduce a lot of the drag. A lot of the energy is being reduced. Energy consumption is being reduced by this head optimization. Other optimizations includes optimizations in the intercarriage gap, whereby instead of allowing that gap to be just a gap that connect two cabins, we also make sure that we smoothly close the gap so as to reduce flow separation. So if we can reduce flow separation in these areas, we can improve the aerodynamic drag. So shape optimization, not just in these in the head shape, or the tail nose shape, or the intercarriage gap. Other optimization are also being done in the bogey regions. So instead of just allowing the bogey regions to be opened, that the body is to be exposed to air, whereby these air, when impacted with the bodies, will cause increase in drag. So what we do is to ensure that we cover these bogey regions. So these optimization also try to helps to improve the aerodynamic process. So other optimization includes active and passive flow control. Active flow control is a method in which we provide external energy, just like we ensure that we put some actuators in some areas where we see that there is flow separation, and then we either either we ensure that either we suppress the suppression this flow separation by using these active flow controllers. And others are passive flow control, whereby we use an external geometry, either fins, or we use spoilers, just as we see in the cars. For example, we use spoilers. These spoilers are meant to spoil, as it sounds, right? To spoil the wake flow. If it spoils the wake flow, or to distort the wake flow. If it distorts the wake flow, then we can ensure a reduction in the drag. Others include bionic surface design. These design are being done in whereby we try to mimic the things we see in nature. For example, the shape of a sheep, of a fish, for example, or the shape of a bird, or any of these things we see in nature, ensure that so as to ensure reduction in energy consumption. So for safety, we can also optimize the shape of the train. We optimize the shape of the train in order to reduce impacts or to ensure that we smooth, for example, the body of the train so as to reduce the effect of crosswind. This will ensure safety when moving in windy environment. Speed optimization. So for speed optimization, we try to design the speed so as when moving in a windy environment or in a unsafe environment, we should the train driver should run in a certain speed. This speed can ensure safety when moving in this environment. Then distance between the two tracks. We also try to ensure to design a distance between the two tracks so as to ensure a safe operation when two trains are moving on these tracks. Also, we try to ensure a reduction in pressure waves due to this meeting when two trains meet. So we also design the tracks so as to ensure a reduction in the pressure waves. Also, we analyze the pressure waves induced by the train when passing through a tunnel. So we also design the shape of the train or the shape of the tunnel by using different kind of hoods, that's tunnel entrance, to ensure a reduction in pressure waves. So as these will ensure safety for a train and also for the surrounding buildings, because we know that micro pressure waves at the external or at the exit of the tunnel can cause a lot of problems to the structure close to the tunnel or to the buildings also which are very close to the tunnels. So for comfort, we try to design the body to reduce noise. So these optimizations that I talk about in the bogie region, in the carriage gap region, will try to ensure a reduction in the noise. A lot of papers have been written concerning this noise reduction by shape optimization. Also, we designed the pantograph to also reduce the noise also. Also, I talk about the bogie region noise reduction. So the vehicle coupling, which is the carriage gap area. And also, we designed the inlets, the air inlets, outlet location for the AC, the air conditioning system, so as to ensure a very good comfortability when for ventilation. Also, we ensure that the flow optimization inside the passenger, we ensure a good flow optimization inside the passenger compartment. So there are a lot of studies that can be done, that is being done when we talk about train aerodynamics. So it just depends on the areas you focus on. Train aerodynamics is a very, very wide area of research. So it's very good. So what are the methods that we use in studying this train aerodynamics? So there are three main methods. These include the full-scale experiment, the wind tunnel test, and the wind tunnel test and the dynamic test can be called the reduced scale test or the reduced scale experiment, because we use a reduced model, a scaled model, to carry out the experiment in a confined environment. This includes either a wind tunnel or a dynamic test rig. And the last one is the numerical simulation. So for the wind tunnel test and the dynamic test rig, if you go to the high-speed research center there, just at the back of the north building, you see the dynamic test rig there. I know that for new students, if you come to Central South University, they will try to take you for a tour in those areas. So that place is used for experiment of train aerodynamics. And then for wind tunnel test, we have two main wind tunnels in Central South here. One is in the high-speed research building, which is the small wind tunnel, and the big wind tunnel is in the civil engineering this thing there, department there, when you climb up there. So these two wind tunnels are being utilized in studying the train aerodynamics of high-speed trains. So for numerical simulation, these are simulations that we utilize series, computer-aided designs to simulate the aerodynamics of these high-speed trains. So for full-scale experiment, what we normally do is to attach pressure sensors, all other sensors like temperature sensors and external humidity sensors at different parts of the trains in order to record these either pressure, temperature, or humidity at different areas. So that is how we do for it. So we attach it. After that, after attaching them, we connect these sensors to a data collection center inside on board the train. Then we carry out this experiment. That's by running the train on a track. So for externally, we can put external devices for also recording the various parameters, which include pitot rig, the pressure tap sensors. These are different sensors that we can also use to record the external flow phenomenon around the train as the train is being operated. We can also attach an anemometer. These anemometer, the sonic anemometer, can record the flow in 3 directions, in X, Y, and Z direction. So it's a very, very good device for measuring the flow around the train as it's being operated. So for reduced scales, for the scale experiment I earlier discussed, we have two different kind of reduced scale experiment. These include the wind tunnel test and the dynamic test or moving model test. So for the wind tunnel test, what we do is that the wind tunnel has been designed in such a way that the train can just be seated in a flat area or in the test area. So that is train, the wind tunnel is being designed such as air is being passed over the train. Okay, so with the aid of pressure sensors, we can collect the pressures or the forces at various parts of the train. So that is for wind tunnel experiment. So we just keep the train on a wind tunnel, inside the wind tunnel, and then pass air. So now, before carrying out the experiment, we have to attach various sensors. Okay, but the wind tunnel is being designed for such things. So when you go to do the experiment, there are some technicians that will help you in arranging the train and various setup so as to carry out this experiment. Also for the moving model test or the dynamic test experiment, also we can what we do is that the train, instead of the train staying on ground, the train moves. Okay, the train moves. So for this experiment is being carried out to study a very few aerodynamic problems. These include when train is moving through a tunnel, or when we want to study the effect of different kind of hoods, that's different kind of entrance design for the tunnel. So most especially for moving test experiment or moving model experiment, we normally use to study the train tunnel aerodynamics. So we studied the train tunnel aerodynamics mostly for the dynamic test experiment. Then for the wind tunnel test experiment, we normally use to study different forces. So such as the drag force, the lift force, and the side force. So this is the configuration. So before you carry out the moving test experiment, what you do is to attach different devices. This include the pressure sensors and the power supply equipment and also other equipment, so as to record that will help recording the different forces on the different pressure or forces on the train body. And also you have to attach also these sensors on the on the tunnel wall, so as also to record the forces on the or pressure on the tunnel wall. So for computational fluid dynamics or numerical simulation, so what we do is to design a CAD model for the to carry out these train aerodynamic studies. So we design a high-speed train. Also, we design a computational domain, just like the wind tunnel. So what we do is that we design a computational domain like a wind tunnel, and also we design the train. So we use, for computational fluid dynamics, we use the configuration of a reduced scale experiment. So we use the configuration of a wind tunnel. Okay, so just like a wind tunnel is being designed, so we design the computational domain, and then we design also the train. So after that, we put the train inside the computational domain, and we apply different boundary conditions. So at the entrance, we apply a velocity inlet, and then for the outlet, we apply a pressure outlet, as the case may be. So, so that is how we carry out computational fluid dynamics. But we know that for we to study this aerodynamic, the problem using computational fluid dynamics, we have to do other extra work. Instead of design, and apart from designing the train and the computational domain, we have to mesh the train and the computational domain. So we have different softwares for doing this mesh. So this can be all be meshed using ANSYS Fluent meshing. We also have tools like Star CCM. We have ANSYS ICEM, and so on and so forth. So these tools can be used in carrying out this mesh operation. So after we have meshed this train and the computational domain, we go on to simulate. Okay, so for simulation also we have different softwares for carrying out this simulation. These include Fluent, ANSYS Fluent simulation package, or we can use Star CCM to carry out the simulation, and other softwares which either open access software or any other software. There are a lot of softwares out there that we can carry out this simulation. So after that, in order to ensure that our simulation is good, we carry out a validation. This validation consists of two kinds of validations. We have numerical method validation and validation of mesh grid, which include the mesh independent study. For mesh independent study, what we do is to compare three different meshes. This include either a fine mesh, a medium mesh, and a coarse mesh. And then we compare the result of these three meshes. So what we do here is to ensure to provide a trade-off between accuracy and computational time. So we want to reduce computational time, and we want to ensure an accurate simulation. So we know that when we have a final mesh, we can easily compute different parameters. We can compute this simulation accurately. But we don't want to use fine mesh, because when we use a fine mesh, we are going to need a lot of time to carry out the simulation. So we ensure that the medium mesh or the coarse mesh can give us almost the same result as a fine mesh. So if this is being done, then we can use the median or the coarse mesh to carry out subsequent simulation. So this is called the mesh independent study. Another validation is to compare your result, your numerical simulation result, with an experimental result. This experimental result can be the full scale experiment or the reduced scale experiment. When the variation between the numerical simulation result and the test and the experimental result is very small, then we can see that our numerical simulation is valid for subsequent work. So, as I said earlier, we have different tools for carrying out these numerical simulation. For the basic tools needed to conduct and train aerodynamic research or simulation or using a CFD method. These include we need some basic knowledge of fluid dynamics or fluid mechanics, mathematics, and computational fluid dynamics. And also we need to know how to design the train or how to model the train using CFD, using CAD tools, which include Rhino, SpaceClaim, and so on and so forth. And also we need to know how to mesh using either a friend meshing package, ICM, Pointwise, Star, CCM, or Meshing, or any other meshing software. And also we need to know how to simulate using simulation softwares using such as Flint, Star CCM, and so on and so forth. Also, we need to know how to make post-processing using some post-processing tools such as ANSYS, Insight, TechPlot, and so on and so forth. Also, we need to know how to analyze these data after simulation. After simulation, we can get quantitative results and also qualitative results. So for the quantitative result, we need to do data analysis. So these data analysis, we need to use tools, which include Excel, MATLAB, Origin, or any other tool for data analysis. So to analyze the results, this result analysis is subject to what you are studying. Are you studying the forces in order to reduce energy consumption? Or are you studying the flow around the train in order to ensure safety, either crosswind safety or crosswind stability, slipstream, and so on? Okay. Or are you studying the flow inside the train in order to ensure also comfortability, or you are studying the flow in order to ensure noise reduction, either internally or externally? So for the force analysis, we analyze the drag force, the lead force, and the fight force. These forces can be exported directly from the software to a file. So we collect the data as the simulation is concluded. We collect the data and then we use any of these analytic software, data analysis software, to analyze the drag forces, the forces, either lead, drag, or side forces. So these will give us an insight on how our optimization or how the solution we provided is good or is valid. So after that, we can make a very good conclusion that, okay, after making such optimization, was able to get the drag to reduce, or the side force to reduce, or the lead force to reduce, or to reduce. Also, we can study the flow distribution. This flow distribution we study to ensure that we know in-depth knowledge on how various optimization affect the flow around the train. And if the flow around the train is being studied, how can we adjust or optimize various parts in order to also further improve the flow around the train so as to provide good optimization. So these will help us to reduce the forces, aerodynamic forces, or to ensure a noise reduction, or to make a different optimization, as the case may be. Okay, so that is why we studied the flow distribution around the train. Also, we studied the pressure distribution. The pressure distribution also will give us an insight how the air impacts on different parts of the train. These will give us a further reason to either optimize the train surface, and also will give us an insight on where and how to make optimization. So this is very important to study. So these are the three most important part that or aspect that you need to study basically when carrying out train aerodynamic analysis, result analysis. So in conclusion, railway train aerodynamic problems are closely related, associated, or related with the flow around the train. So these problems are mainly because of the flow around the train, and with the increase of train speed, many engineering problems which have been neglected at low speed are being raised. So many problems that we did not see when the train is moving at a very low speed start to come up when we are moving the train in high speed. These problems include energy consumption, safety, comfort problems. So train aerodynamic research or studies aim to provide solution to various aerodynamic problems in order to improve the high-speed train operation. Yeah. So this is my presentation. So if you have any question, you can ask. Thank you for listening.
Thank you very much, Malik, for such a sumptuous presentation. So I will urge the audience to feel free to ask Abdulmalik. This is his field, so you can feel free to pose your questions. So if you want to ask any questions, you just raise up your hand, and then I'll just allow you to speak. Malik, I have a question.
Okay.
For others start. Is there any significant influence of the what do you call it? Like the domain? Is that, I think there's a name. I've forgotten the name, sorry.
Computational domain.
Sorry?
You mean the computational domain?
Yes, the computational domain. Is there the size of the computational domain? Is there a significant influence of the size on the pressure or velocity distribution inside?
Yes. There is a significant.
So what do we say is the optimal for what kind of model? Yeah. So compared with the size of the model, what is there any advice you can give us with regards to the optimal size of the computational model?
All right. So this is a very good question, because these computational domain, size of computational domain really affects the study, the flow dynamics inside the computational domain. That's why there are a lot of studies that study the aspect ratio. Aspect ratio studies on the various, not just some train aerodynamics, also various vehicles such as Ahmed Body, GTS, and so on and so forth. So how much should we size the computational domain? So for high-speed train, there is a standard. We have a standard that will give us guide on how to design the computational domain. So the size, the width, the height, the length, the sizes are being mentioned in these standards. So when you want to study high-speed train aerodynamics, I'll advise you to first go through the standard. Read the standard first, okay, so you know on how to perform the various steps of carrying out this study. Okay. So because for me, I studied the ICE 3 high-speed train. So the ICE 3 high-speed train is a German train that runs in Germany and other parts of Europe. So this train, to study it, you need to read the EN standard, okay, the European Union standard. So this standard will guide you on how to design a computational domain. However, a bigger computational domain is better. The bigger the computational domain, the good, the better. But the problem you are going to encounter is as you increase the size of the computational domain, the size of the mesh is going to increase because you're not just meshing the surface, you are also meshing the flow inside the computational domain. I don't know if you understand. So you have to design the computational domain in a sense that it's not too big and it's not too small. It's not too big so as not to so that you don't need to have plenty of mesh, because if you have plenty of mesh, then you need a lot of time to carry out the simulation. Can compute this to be actually have been answered for high-speed trains, either for what's it called it, either for the time these high-speed or to study the effect of aspect ratio. Okay, so you can go and read the study and determine the size of the computational domain that you should use to carry out your simulation. Yeah. Thank you very much for that.
Thank you. I was hoping you could give like a general relationship, like between the size of the computational domain and, for example, the wind strength inside, like, or the velocity, the velocity distribution, magnitude of the pressure, for example. Is there like a direct relationship?
No, not really, actually. Not really. But we know that.
Let me give a classical example.
Okay.
A classical example. For example, if I'm doing moving mesh, simulation.
Okay, yeah.
So I have this particular scale or size of computational domain, and then my moving mesh model displaces by, let's say, 2 meters, for example, 2 meters. If now considering the size of the computational domain, what do I do to what variation of the size of the domain of the computational domain can affect this displacement of the moving mesh model?
I don't really get you.
Like if you were to increase the computational domain, will it affect the displacement of the moving mesh model?
If you increase the size of the computational domain?
Yeah, and then the displacement of the moving mesh model.
Definitely, when carrying out dimension. Okay.
Hello, we can't hear you.
Your computational domain is going to be bigger.
I think your network is a bit
because you are going
problematic.
to definitely, because the size of you. Sorry. Can you hear me now?
Yeah, we can hear you now.
Okay. So when carrying out a dynamic simulation, okay, especially the simulation you talk about, the moving mesh simulation, you need to have a very big computational domain. So, but for dynamic model, for dynamic simulation, because we need to transit the train from one position to another position, you need a bigger computational domain. But you need also you need an interface that will provide the moving mesh, okay, between that's the internal interface and the external interface. So the computational domain is totally different compared to this one. That one is going to be bigger. So if you are meshing, it's going to have a lot of mesh. So for this one, if for example you are having maybe 12 million cells, for that one it may be multiplied by 2, depending on how big is your computational domain. And then for that one, you design the computational domain such that when you transit the train from one position to another, it covers the distance you want to cover. Okay, so there is a very a big difference between this and that. I don't know if you get me.
I get it. I get it.
Yeah.
Thank you very much. Are there any other questions from the audience? Okay, I'll wait for 5 seconds. After 5 seconds, I'll assume that there are no questions. All right. In the absence of any further questions from the audience, I would like to use this opportunity to thank you very much, Abdulmalik, for your time and for your knowledge, for sharing. Thank you very much.
Thank you very much for having me.
Okay, this is the end of this session. I hope you keep you stay tuned for tomorrow's and other future presentations, everyone. Thank you very much, and this is the end of the session. Bye.